Okay, in the last video, we introduced the substitution technique to solve integrations of these various forms here for rational trig functions, and we want to use it specifically to solve this integral of dx divided by 2 times the sine squared of x plus 4 times the cosine squared of x. So let's look at the denominator here. 2 times the sine squared of x, this is going to be 2 times z squared divided by z squared plus 1, and we have plus 4 times the cosine squared of x, so that would be 4 divided by z squared plus 1. So this is just going to come out to be equal to 4 plus 2 times z squared divided by z squared plus 1. And this is in the denominator of this integral. So let's see. We're going to rewrite the integral then. We're going to have z squared plus 1 divided by 4 plus 2 times z squared, and dx is this. That's dz divided by z squared plus 1. And let's make some room here. So these cancel, and we have the integral of dz divided by 4 plus 2z squared, and I'm going to factor the 2 out of there, so it's going to be 2 times 2 plus z squared. And again, this looks like it's all set up for a trig substitution of this type, where the secant squared of theta equals 1 plus the tangent squared of theta, a constant plus a variable squared. Constant plus a variable squared. These are the same general format. So then we say, let this variable z, let z be equal to the tangent of theta times the square root of this number. So that would be the square root of 2. And dz, let's take care of that while we're at it. dz will be equal to the square root of 2 times the secant squared of theta, d theta. So we should be all set, really. What we have to keep in mind is that we got to this stage, we started with this integral, we made this substitution, which got us this integral, and now we're introducing yet another substitution to solve this integral. And we'll rewrite it. dz, that's the square root of 2, times the secant squared of theta, d theta, divided by 2. Make this a little bit bigger. 2 times 2 plus z squared, 2 tangent squared theta, and of course you see why we chose this coefficient here to be the square root of this number, so that when we do our substitution here, this number appears across the expression and we can factor it out. So here we have square root of 2, integral of secant squared theta divided by 2, factor out this 2, times 1 plus tangent squared of theta, and we have d theta from up here. And this is the secant squared of theta. So it looks like we're going to have 2 divided by 2 is 1 over the square root of 2, so we'll have 1 over 2 times the square root of 2, the integral of d theta. Of course, that's just going to be theta. And what is theta? We go back to this substitution, and we see that the tangent of theta, that equals z divided by the square root of 2. So we can say theta equals the inverse tangent. The tangent of theta equals this. Theta will equal the inverse tangent of z divided by the square root of 2. But let us remember, z is the tangent of x. That was our substitution. So we can say theta equals inverse tangent of the tangent of x divided by the square root of 2. So we had this times theta, and theta is inverse tangent of x divided by the square root of 2. So again, we went through several variable changes. This is the one that sets us up. So you can transform this integral into this integral. Then we made this variable change, so we'd have solved this with a trig substitution. And that came out real easy. That was just the integral of 1 over 2 times the square root of 2 d theta, once we got finished doing our simple manipulations here. And theta is this. And this is theta. And that's it. So, integral dx divided by 2 sine squared of x plus 4 cosine squared of x. That's 1 over 2 times the square root of 2 times the inverse tangent of the tangent of x divided by the square root of 2 plus a constant. Okay, as you can see, it took a couple of substitution steps to get there, but really all the integrals that were involved along the way were pretty simple. So this can be a pretty handy technique to use. Come back and we'll see if we can solve some more problems with it.